is equal to ypx minus xpy. So here it is. We're doing well so far. Now we want to plug in our definition of the momentum operator. Now here's the thing that I want to explain really quickly. It's confusing to write this because this has no meaning. Momentum is a number. A number can't be equal to an operator. So what actually is this? This isn't momentum. Well, we call it the momentum operator because it's useful. It's a tool that we use to extract the momentum of any particular object. All we have to do is find the expected value. All we have to do is find the eigenvalues and eigenfunctions of this operator. And the eigenvalues in specific tell us what the actual momentum is. And you know, eigenvalues are always scalars. So you can ensure that this actually makes real world sense. This chalk is falling apart a little bit. Okay. Is it peeling off? That's weird. Anyway. So, now that we know that, these are the actual definitions of angular momentum in classical mechanics. In quantum mechanics, I am not writing down the angular momentum. I am writing down the angular momentum operator, which helps us find the angular momentum. So we get Lx operator is z times minus IH bar partial y minus y minus IH bar partial z. Ly x minus IH bar partial z minus z minus IH bar partial x, and Lz is y minus IH bar partial x minus x minus IH bar partial y. Now, factorizing and rearranging this guy gives us the Lx operator is factoring out the IH bar and applying the negative. Y partial z minus z partial y. Y operator is IH bar z partial x minus x partial z. And Lz operator is IH bar x partial y minus y partial x. So there we go. We've successfully written out the three angular momentum operators. There we go. We're going to be using these definitions for the rest of today. But now, where do we go from here? Well, we want to find the eigenvalues of these guys. But that's not all. To talk about a particular system, we want to know about eigenstates of all of the measurables within it. So, Lx, Ly, and Lz are obviously measurable quantities. Now, the tricky thing with quantum mechanics is that there are uncertainty principles. Our ability to measure two measurable quantities, A and B, is only as good as the commutator of their corresponding operators is. I should probably put an absolute value on that, but who cares? So, if this commutator is non-zero, thank you. Sorry. So if this commutator is non-zero, what does that tell us? It tells us that if we have an accurate pinning on 1, well, we'll never have an accurate pinning on 1, because that would require infinite uncertainty on the other, which is simply not possible. But the more accurate we get on one, the less accurate we get on the other. But the fundamental thing is that we will never be totally accurate with either of the two, let alone both. But if the commutator is 0, that means at some point we can be certain about both quantity A and quantity B. That's the cool part about the generalized uncertainty principle. So we call any measurables with corresponding operators that have a 0 commutator compatible observables. So right now, and sorry, what are these compatible observables good for? Well, because we can know both of their corresponding observables with all the uncertainty we need, including 0 uncertainty, that means we can find an eigenstate, i.e. a physical reality, that gives us a 100% accurate picture of both operators at once. We can find a valid eigenstate for both of the two. But if said observables are not compatible, our hopes of finding compatible eigenstates are dashed. So, which of these are compatible with one another? Are any of them? Well, since these guys are the same up to cyclic permutation, what I'm going to do right now is find the commutator of Lx and Ly and generalize results from there. So, what is the commutator of Lx and Ly? Well, I mean, they're operators, which means that just writing this out doesn't tell us anything. We have to actually apply it to a test function in order to know what it does. So what happens when we do so? We get Lx Lyf minus Ly Lxf. And so what happens when we expand this? Well, this is going to be messy, to say the least. First things first, notice that we have to factor out IH bar times IH bar, because so that means there's going to be an IH bar squared lying out in the open. Maybe over here instead. It's never too much space. So we have over on this side what's going on. Well, Lx is going to give us y partial z multiplied by Ly is going to be z partial x minus z partial xf minus x partial zf. And then you have minus z partial y times the same exact thing. It looks like we're going to have to move this to the second line. Minus, how are we going to go about this? Z partial x times y partial zf minus z partial yf plus x partial z y partial zf minus z partial yf. Good. Now what do we do? I don't want to erase this. Well, there's nothing we really can do other than expand this with all of the messy partial derivatives. And what follows as a result? Well, we're going to get IH bar squared, or minus H bar squared. I'm going to leave that all the way to the left side, so everything else will get ready for the carnage. And what's in here? Oh boy. We get y partial z, so partial z of whatever's inside this is going to be partial xf plus z partial x partial zf. And then there's going to be minus an x partial z squared f, and then minus z times partial y of this, which is going to be z partial x partial y f minus, there's no y term here, so it's going to be x partial y partial z f. And then, over on this side, it's going to be minus z partial x times, there's no x term, so y partial x partial z f minus z partial x partial y f. You will notice some reappearances, so keep track of those. Plus x, there's a z term right there, so y partial z squared f minus partial y f minus z partial y partial z f. Okay, we're doing well so far. Now, what we're going to do is look for a factorization. Since you probably already noticed, there are a lot of common terms here, a lot of common factors. So we get minus h bar squared times, first let's factor all the terms containing partial xf. Actually, I didn't notice any repetition of it, so perhaps this is the only one. Next, all the terms containing partial x partial z. There's a yz here, xz, xz, oh, here it is, minus zy. Of course, what is that if not, 0. Next, we have a partial z squared f. I see a minus xy or a minus yx here. And is there any other appearance of it? Yes, right there, where it says plus xy. That is also going to give us a 0. Next, there's a partial x partial yf here. There's a minus z squared term in front of it here. And there is a plus z squared term in front of it here. Yes, that is also going to give us a big fat 0. Then you see the yz term. Factor this guy out. You see a zx term here first. Then over here you see a minus xz term. That also goes to 0. We already covered this, we already covered that, we already covered this, and that only leaves the minus x partial y. And we already covered that. Which means that, after all of the dust settles, the commutator of Lx and Ly operators applied to f is equal to minus h bar squared multiplied by y partial xf minus x partial yf. And of course, since we can factor out the f here, we can oblige in removing it to state that the commutator of Lx and Ly is minus h bar squared y partial x minus x partial y. Hey, wait a minute, that looks oddly familiar. So we can write this as I h bar squared multiplied by x y partial x minus x partial y, which means that it's just minus IH bar LZ. It's actually supposed to be plus IH bar LZ, but we'll ignore that sign error. And what does this tell us? Well, it tells us that the commutator of Lx and Ly is IH bar LZ. So, by cyclic permutation, Ly LZ is going to be IH bar Lx. LZ and Lx is going to be IH bar Ly. So, of those are telling us that unless one of the components is equal to 0, none of these three are compatible with one another. Aw, shucks. But not all of this. Sorry, thank you. So these three are not compatible. But let me tell you what is compatible. The natural next step is to try, and by the way, these are still useful, so I'll keep them around. I can erase this part instead. I'll tell you what things. Let's change the other two by second. Let's erase this. I'll tell you what is compatible. The natural next step is to try the magnitude of L. But that's the square root of Lx squared plus Ly squared plus Lz squared. Now, given that 2 centuries have been dedicated to finding out what the hell this means, and we still haven't got a concrete answer, and given that this is hundreds of times more complicated than just that, I think that it is advisable to not explore.
Can you repeat that last thing? 200 years?
Yeah. So given that we've spent 200 years just trying to figure out what the hell this could possibly mean, stepping into something 200 times more complicated than that doesn't seem too approachable to us, at least at first glance. So we're going to rule that out for now. Instead, how about we try the norm squared? Applying something twice is a lot easier than figuring out what it means to apply something half. This is just Lx squared plus Ly squared plus Lz squared. Incredibly easy to define, at least compared to the ungodly square root monstrosity. Which means this is what we're going to go with, that observable. Will this observable be compatible with any of the components? Well, let's try with x. Now this, since L is a linear operator, can be broken up into Lx squared Lx plus Ly squared Lx plus Lz squared Lx. This is just the distributive property looking a little bit weirder. Now, what we're going to do is, first of all, figure out this is just Lx cubed minus Lx cubed. Operators always commute with themselves, which means this is just going to be 0. And what about the other two? These two aren't the same, and Ly isn't Lx. So what happens? Well, this is where this guy comes into play. So how do we actually write this? Because we know what the commutator of Ly and Lx is, but we don't know what the commutator of Ly squared and Lx is. Well, here's the good part. What is this? Well, we can rewrite it as a squared b minus ba squared. Now, at first, it's tempting to see how close we can get by writing ab minus ba times a. Or either this way or that way. But here's the thing. If we write it this way, we get a squared b minus aba. Remember, operators don't commute with other operators unless we're under very specific circumstances. And if we apply it the other way, we get ab minus ba times a. Well, that's aba minus ba squared. Hey, wait a moment. If we just add these two together, thank you. If we just add these two together, the problematic terms cancel out, and the ones we need stay. Okay, hip hooray. Which means that we can just rewrite the commutator of a squared and b is a times the commutator of a and b plus the commutator of a and b times a. Alright, so what happens when we do that here? We get Ly times the commutator of Ly, Lx. And what does this become? Well, it's just this, but flipped. That's how commutators work. When you flip the order, you get a minus sign. So, they're skew symmetric, if you like to say things that way. Then you have plus, well, minus I h bar Lz times Ly. These two do not commute. These two do not commute. But that doesn't change the end result anyway. And the same thing happens here, but instead, this time it's in the correct order, so we don't need to flip signs. We get plus Lz multiplied by IH bar Ly plus IH bar Ly Lz. Now notice, scalars always commute with operators, no matter what. Which means that we can bring the IH bar here to the outside. And we can bring the minus IH bar here to the outside. So, taking off the parentheses and simplifying as much as we can, we get minus IH bar LYLZ minus IH bar LZLY plus IH bar LZLY plus IH bar LYLZ. Holy crap, it's all 0. Which means that the magnitude of L squared actually commutes. So, this guy and these three are compatible. So, that's good. You want to know what's not good? Nothing. So far.
Baby, drink the water, sorry. This takes so much energy to do this.
Sorry. Okay. So, these are compatible observables. What I am going to do now is try and find, we just talked about finding an eigenstate for two compatible observables. What if I find an eigenstate that works for both L squared and some component of L? Now, I'm going to save the first two components for our raising and lowering operator. It's a little bit of spoilers. But I'm going to pick LZ as the component we're going to try and find a compatible eigenstate for, along with the magnitude squared. But first, while I'm erasing, take a moment to appreciate the physical meaning of this. We will never be able to figure out the direction of the angular momentum vector unless we already know it's 2D. However, we will be able to figure out the magnitude of the vector. And not just that, we'll even be able to figure out one of its components alongside it. Alright. Great. I don't know why I'm uncapping my marker. You can't use markers to write on black paper without great difficulty, of course. So, how do we find eigenstates? Well, simple on the surface. We just have to find an eigenfunction that satisfies both this and that. And then lambda 2 becomes associated with LZ, And lambda 1 becomes associated with L squared. Okay, so how do we do that? Well, things are not that simple. Because this is pretty much impossible to solve regularly. Until we know what the eigenvalues might actually look like, this is pretty difficult to look at. So let's try and solve for the eigenvalues first, while totally dodging the subject of the eigenfunctions. So, oh, it's crumbling. How do we find the eigenvalues? Well, here's a trick. We tried to find eigenstates that satisfied the Schrödinger time-independent equation using a ladder, where we could go up one rung by applying L plus a raising operator, or back in those days it was A plus, to the wave function, and we could lower one rung by applying A minus. And we could keep going up, or we could keep going down, until we hit some top or some bottom. Of course, what those tops and bottoms are will change. And of course, the raising and lowering operators are going to change. I already spoiled them, but L plus minus is Lx plus minus ILy. This hopefully looks familiar. So, now that we have this, since the ladder operator uses these two, it becomes a wild hassle to try and figure out compatible eigenstates for L in any of these two. So, what we're going to do instead is work with LZ, because it makes our commutator magic work really nice. So, what do we do in this situation? Well, okay, so this is pretty hard to solve by itself. We're going to assume we've already found a solution. What that solution actually is, we'll delegate to the future. And we found an eigenvalue to go along with it. Shit. So, now that we have that, we're going to see what happens if we try to construct more solutions from there. So, how do we start? Well, these raising and lowering operators are going to be what helps us construct more solutions. We're going to claim that we know this works for some f naught. I now claim that L squared L plus f naught also works for a different eigenvalue. It doesn't necessarily have to be different, actually. I claim that L plus f naught is also an eigenvalue. Now, how do we prove it? Well, it's pretty simple in this case specifically. Any operator always commutes with a scalar. Meanwhile, an operator doesn't have to commute with L squared, but L plus in specific is a linear combination of Lx and Ly, two angular momentum components which are compatible with L squared, which means that it does commute with L squared too. So this tells us that L squared f naught is equal to lambda 1 prime f naught, which, is equal to lambda 1 f naught, which implies that lambda 1 prime is equal to lambda 1, unless f naught is equal to 0, but that doesn't describe the angular momentum system very accurately. So, lambda 1 prime is equal to lambda 1. Simple as that. Which means that no matter which way we go, up or down, no matter if we apply the raising or the lowering operator, the magnitude is going to stay the same. We're never going to find a solution with higher total magnitude. But what happens with LZ? We've probably already figured out it's not going to be that simple because LZ doesn't directly commute with L plus. This is where commutator algebra gets a little bit funky. So we have LZ L plus F naught is equal to lambda 2 prime L plus F naught. What is lambda 2 prime? Well, first we commute these two. And here is where we can really take advantage of commutator algebra. These two don't directly commute. So why am I writing L plus LZ F naught? Well, because I'm immediately going to subtract L plus LZ F naught. And then I'm going to add what we were originally talking about, LZ L plus F naught. But in doing so, I've basically written L plus LZ F naught plus the commutator of LZ and L plus F naught. And now it is time to get funky with commutator algebra. So, LZ L plus is more like LZ Lx plus I LZ Ly. Once we use the distributive property, and we know what these two are. By cyclic permutation, this becomes I H bar Ly, and this becomes I times minus I H bar Lx. I times minus I is 1. And when you look at that, it's just H bar L plus. Okay, interesting. Which means that if this is H bar L plus, since operators always commute with scalars, we can write L plus Hf naught, H bar F naught, is equal to L plus lambda 2 prime F naught. Or in other words, LZ F naught plus H bar F naught is equal to lambda 2 prime F naught. Now, lambda Z F naught, we already assumed is equal to lambda 2 F naught. Thank you. I'll leave that for later. Which implies that lambda 2 plus H bar is equal to lambda 2 prime. Wow. So we can always construct new solutions that either raise or, if we use the lowering operator instead, lower the z component in specific. But of course, you can also run into a contradiction here. I mean, if I tell you the total magnitude of the vector is 5, and the z component is 6, this doesn't make sense. Because then that implies that the magnitude has to be at least greater than it is. Which means that LZ cannot be greater than the magnitude of L. LZ squared has to be less than or equal to L squared. Another thing. This also wouldn't make sense if it was minus 6, but I guess that's covered here too. So plus minus LZ has to be less than or equal to L. Okay, so that's fairly straightforward.
How much longer, baby?
A lot longer.
So you drink water, please.
Okay. So what does that imply? Well, since we run into a paradox if we make LZ too big, by repeatedly applying the lowering or raising operator, that means there must be both a clearly defined bottom and a clearly defined top. Now, we also had a clearly defined bottom, though not a top, when we were talking about the time-independent Schrodinger equation. And how did we enforce the border? Well, we said if if you have the top function, ft, or the bottom function, fb, if you apply the raising operator to ft anymore, or you apply the lowering operator to fb anymore, you will get a big fat 0. And so, basically everything past that point is null and void. So that tells us a lot about what ft and fb are going to be as well. And of course, it tells us a lot about the eigenvalues. So what happens if we know this? And what happens if we know that? How do we proceed with this knowledge? Okay. Alright, so here's what we're going to do. We're going to say that L plus or ft, let's take the rung right below it. ft minus 1 or something, I don't know. And so let's say we have L plus of this. That's going to be equal to lambda something of this. Now I ask you, what is this lambda going to be? Right now, I'm going to say it's equal to m times h bar. We know absolutely nothing about this m. It could be any number in the universe. It could be irrational, it could be transcendental, it could be rational, it could be an integer, it could be a half integer. I'm kind of spoiling things. It could be anything. So, we don't know anything about this, so saying lambda is equal to this is a perfectly valid statement. This could even be 0. Well, actually it can't be 0, because, you know, this is the rung right before the top. It's not supposed to be 0, it's supposed to give us the top. So, we have this, right? But here's the thing. Once we get to the top, right after it, we're going to hit a 0. And the same way, once we hit the bottom, we're going to get a 0. We're going from a 0 this way to a 0 that way in an integer number, let's say n, steps. And on each step, we're going h bar this way or h bar that way. Which means that in total, that means that the max eigenvalues are plus minus n over 2 h bar. Integers or half integers. And everything in between is just n over plus minus n over 2 plus minus some integer n. That's it. We figured out the eigenvalues without ever knowing anything about the eigenfunction. But, of course, to actually solve this equation, we need to know about the eigenfunction. So, how do we do that? This is just part 1 of 2 parts. How do we find the eigenfunction? Well, first things first, we're going to convert to spherical coordinates. Now, we're going to first reflect on what L is. What is this? Well, P is IH bar partial X, IH bar partial Y, IH bar partial Z. Oh, sorry. Now, factor out the IH bar. Sharpen visuals. Hey, wait a moment, that's just the gradient. There we go. P is the gradient. So, in essence, we're working with IH bar, the curl of R. Hopefully this looked familiar to you. But, what is that curl in spherical coordinates? Oh boy. Well, we're going to get IH bar times partial R plus 1 over R partial theta R plus 1, R hat dot R partial R plus 1 over R multiplied by theta hat times R partial theta plus phi hat dot R over R sine theta multiplied by partial phi. Now, first things first, this becomes, well, this is just R multiplied by R hat times R hat, which is 1. Second, R over R the vector over R the scalar, is just R hat. So this is what? Sorry, this should be cross. And, you know, a vector cross itself is 0. This should disappear. So this is theta cross R over times partial theta. And this is phi cross R. Since this R disappears, because R, the vector over R the scalar, is R hat, multiplied by cosecant theta, partial phi. Notice that we can reduce this guy to phi hat and this guy to minus theta hat. Okay, so things are all nice, happy, and joyful. No, they aren't. What do we do with this? Well, at this point, we want to convert these guys back to their Cartesian forms. But how do we do that? Let's see, how do we actually convert partial theta back? Wouldn't it be... It's going to be the chain rule. So, partial f partial theta is equal to partial f partial whatever times partial whatever partial theta. So we're going to have this plus partial y partial theta partial f partial theta and partial z partial f. Oh, sorry. Partial f partial y. Okay, so now I just need to figure out which plane theta is in. I think it's the xy plane, which means we should be fine with this because partial z partial theta should be 0. Okay. So now we just have to figure out what partial x partial theta and partial y partial theta are, and we'll be all set. So what are those? Well, theta, at the end of the day, is equal to arctan y over x. But what is x? Well, actually, no. We shouldn't write it this way. X is cosine theta. Hold up. X is r cosine theta, and y is r sine theta. Which means taking the derivatives with respect to theta just gives you this is going to be minus r sine theta partial x f plus r cos theta partial y f. Okay, there we go. Now a similar thing happens for partial phi, but instead partial phi is in a different plane. How would I describe it? Partial phi is kind of in the theta z plane. So how would you write partial phi instead? I am not remembering my spherical to Cartesian conversions. Okay. Well, if I draw a point over here, this is theta, but this is phi. Or this is phi. Which means what? Well, converting this back to x, y, z means what is phi? Well, x, it's actually a lot more simple than I'm thinking. X and y have no dependence on it. Phi is just, z is equal to r sine phi. Which means that, I'm missing something. Do you want me to leave it here?
Yeah, leave it here.
Alright. Thank you everybody for watching, and we'll see you in the next one. Okay, so I'll just remember.